Welcome. I'm Jim Stock. I'm Vice Provost for Climate and Sustainability at Harvard University and the Director of the Salata Institute.
Today, we're going to focus on the science of sea level rise and melting ice sheets. Because of warming temperatures and oceans, the planet has already experienced some sea level rise, and this will increase. Personally, I feel like this is one of the toughest areas for non-climate scientists to understand, at least it is for me. How much will sea level rise? How do we think about the effects of what seems to be a small amount, like 30 centimeters, about a foot? How quickly will sea levels rise? How much is already baked in as a result of emissions that have already happened? How much can we affect in the future? So there's lots and lots of questions. Fortunately, we have two experts here to provide us with a primer and a guide to some of these issues and to share their research. Jerry Mitrovica and Fiamma Straneo, both of whom hold joint appointments in the School of Engineering and Applied Sciences and in the Department of Earth and Planetary Sciences in the Faculty of Arts and Sciences. Jerry Mitrovica is the Frank Baird Jr. Professor of Science. Jerry's work includes the relation between sea levels and variation in the structure of the Earth's mantle and crust. Jerry is also a participant in one of the Salata Institute's climate research clusters on sea level rise and human impacts in West Africa. Fiamma Straneo is the Gordon McKay Professor of Environmental Science and Engineering. Fiamma is new to Harvard this year, and we're super excited to have her here. She's a physical oceanographer and a world leader in making observations of melting Greenland glaciers and doing the complex modeling to understand their impact on ocean currents and climate systems. We'll start with presentations, first by Jerry and then by Fiamma, then turn to questions. I have some pre-submitted questions, but if you have questions as we go, please use the Q&A feature. So with that, let me turn this over to Jerry.
Okay, thank you, Jim. Thank you very much. I like to start my talks of this type with a simple pop quiz that sort of reinforces one of the main areas or themes of my research over the last couple of decades. So let's begin. I'll ask you rhetorically, what would happen to sea level in Boston Harbor if enough ice melted from Greenland to raise global average sea level 1 meter? Well, in that case, sea level would only rise about a third of that, 0.3 meters. And now we can ask the same question about the Antarctic. What would happen to local sea level in Boston Harbor if the Antarctic ice sheet was to melt sufficiently to raise global average sea level 1 meter? The answer there is 1.3 meters. More than 4 times the amount of sea level rise would occur with Antarctic melting as the same melting from Greenland. Now, the effect on sea level of ice sheets and glaciers as they melt is one of the foci of my work, but there are many different mechanisms that produce sea level rise and make it such a complex area to study, as Jim talked about. Of course, there is the melting of ice sheets, melting of glaciers. There's also changes in ocean properties like temperature, salinity, interactions, winds, and high and low pressure areas that change ocean levels because of atmospheric fronts moving across. And there's also migration of groundwater, both naturally, seasonally, and over long term, but also due to anthropogenic effects like artificial reservoirs. All of these things change sea level, and all of them have a very strong geographic variability that's associated with them. I'm going to focus now on maybe giving you some insight that will answer the pop quiz question, and then I'll move to a more general discussion of sea level. Well, I asked, what would happen if happen to sea level globally now, not just in Boston Harbor, if the Greenland ice sheet was to melt? Now, one might think intuitively that sea level would go up as in a bathtub. That's sort of reinforced by this picture to the right, and that sea level would rise relatively uniformly. But that isn't even close to being true. And it's not close to being true in part because of Newton's laws. This is classical physics, right? The picture on the right here shows in a before and after picture, the before being the dashed black line, the after the red line. When an ice sheet melts, 3 things happen, at least 3. 3 obvious things happen, let's say, right? The first is because now you're unloading the crust, the ice sheet is being reduced in size, the land pops up. And you can see that by the uplift of this dashed line to the red line, the land moving up. The second, somewhat subtle, let's say, effect, although it's very large in practice, is that as an ice sheet diminishes in size, its gravitational pull on the ocean is reduced and water migrates away from the ocean. Now, when that ice sheet is melting, there's certainly more ocean mass, meltwater is entering the ocean, but these two effects of the crust rebounding and gravitational weakening and movement of water away from the ice sheet means that close to the ice sheet, sea level will actually fall. And if you were to raise global average sea level by a meter, melting Greenland ice sheet, that fall is dramatic. It's as much as 10 to 20 meters of fall at the shoreline of Greenland. But you pay the price somewhere because the average has to be, in this case, 1 meter, for example. And that is that as you move away from the Greenland ice sheet, sea level will rise by progressively greater amounts. And here's an image showing you a computer simulation of that effect. Greenland melting enough to raise global average sea level a meter. The red zone there is the region in which sea level will fall. And that isn't a small region. It extends about 2,000 kilometers or about 1,200 miles from the Greenland ice sheet. And you can see, roughly speaking, as you move away from Greenland, the sea level rise that you will experience increases. So that if you were to have a home in Tierra del Fuego at the southern tip of South America, the sea level rise there would be 1.4 meters, 40% more than the global average. Whereas if you had a friend in Scotland and you told them that the Greenland ice sheet were to catastrophically collapse, they shouldn't be that concerned, well, except in a general humanistic sense, because sea level would not change in Scotland, or in fact, it would go down a little bit if Greenland ice melted. Now, the same thing is true of the Antarctic. Melting from the Antarctic will push water northwards, and it has its own unique geographical variability on sea level. And the fact that each glacier and each ice sheet has that distinct variability has meant that these sorts of figures that I'm showing on the right here have come to be known as sea level fingerprints. And with the understanding or the deepening of our insights into this sort of fingerprint world, sea level research has gone from trying to estimate global mean sea level, which I'm going to talk about in a minute, to now trying to understand the regional variability in sea level a little bit better. After all, if each of these things have distinct fingerprints, it gives us a possibility of looking at sea level variability and actually determining not just how much sea level has risen in a global average sense, but where it's coming from. Okay, so now we can go back to this picture. I've talked about this particular case of ice sheets melting. As I said before, there is variability in all of these processes. None of the processes that are on this diagram lead to anything like a uniform change in sea level. But the determination and the understanding of these fingerprints has helped us to go back now and reanalyze 20th century sea level. So in the next few slides, I'm going to talk about the results of that reanalysis, all that's been done in the last 5 or 10 years or so. What's happened in the last century to sea level? Well, sea level is measured in two ways. On the left, it's measured through tide gauges. These are relatively low-tech devices, a cylinder which has a sort of ping pong ball in the middle, and as sea level goes up and down, the float goes up and down, and you just keep a measurement of sea level by determining where the float is, right? One of the problems with tide gauges is they're only sparsely distributed, and they're mostly in the northern hemisphere, which limits the power they have in determining these individual fingerprints. On the right, you have satellite altimetry. So altimetry with satellites has been going on since the early 1990s. So they aren't as their time duration is less than tide gauges, which can extend back a century or more, but they have advantages of an almost continuous monitoring of the sea surface, at least up to high latitudes, plus or minus 60 degrees. They don't really see sea level at the poles. Okay, so using the tide gauge data now, a paper here in 2011 estimated that global average sea level rise was about 1.5 millimeters per year. the same sort of literature showed using satellites now from the early 90s until 2010, in this particular figure, 2014, that on the basis of satellite records, in the last 20, 30 years or so, sea level rise has been about 3 millimeters per year. Okay, so taking these two things into account, the tide gauge measurements and the satellite measurements indicates that there has been an acceleration, a factor of 2 increase from the 19th to the from the 20th to the 21st century, and there's a number there for the acceleration. But okay, now that we understand fingerprints a little bit better and geographic variability a bit better, and we can apply some more complex statistical methods, we can ask, is this value of 1.5 millimeters per year over the 20th century correct? And the fact is, no, it was an overestimate. New estimates based on fingerprint physics show that in the 20th century, sea level did not rise by 1.5 millimeters per year or up to 2 millimeters per year. In fact, it rose by, on average, something much closer to 1 millimeter per year. Now, this might seem like good news, but it's not good news because nobody disagrees with satellite estimates of sea level change. So if you've reduced your estimate of 20th century sea level change, you've thus, by implication, increased the acceleration of sea level that we have experienced in the globe from the 20th to the 21st century. That number at bottom left is twice the acceleration that was previously computed. Okay, where do we go with this? What do we do from here on in? Well, the field has moved well beyond global mean sea level estimates. And after all, if you're an urban designer, a coastal engineer, you're not going to really care about what the global average sea level change has been. You want to know something about sea level in your backyard, both what it was in the 20th century and what it will become. So I'll talk about those things next. There's been a whole large group of studies now that have combined all available information, whether they be satellite altimetry or gravimetry, ocean temperature changes, salinity changes, tide gauge, etc., to try to understand how sea level has varied regionally and locally during the 20th century. This is one such paper. The plot here on the left is really just a repeat of the plot I showed earlier that indicated over the 20th century sea level rise would be on average 1.0 to 1.2 millimeters per year. But what you see in the 6 plots on the right is that now we can take that estimate and we can break it up into oceanic regions like the South Atlantic, the Indo-Pacific, etc. In those, the blue areas, the blue curves represent a reconstruction of sea level based on putting all this data together. The sort of reddish curve represents the contribution to that from melting of ice sheets and glaciers, and the yellow-orange represents the contribution from ocean dynamics and thermal expansion of the water. I'm not going to expect you to understand the details of this, but you can already understand one aspect of this. If you look at frame F and G here in the North Atlantic, you'll notice that it's only in those 2 frames where melting of glaciers is dominated by ocean dynamics. And that should give you a tip-off. If in the Northern Atlantic you see that melting of glaciers and ice sheets is not producing as much sea level rise as it is elsewhere, that's a tip-off that the Greenland ice sheet has been melting, because with Greenland melting, the North Atlantic will see less than the global average sea level fall. Well, we can take this a little bit further, and we can now, with the same analysis, break this up not just into regions, but locally. We can look here, and again, I'm not expecting you to look at the details of this, but here are curves, for example, for San Francisco, Brest, Nagasaki, etc., broken up yet again into these individual contributions. This is a far cry from these earlier estimates of global mean sea level. We've come a long way from this. But let me show you the power of these methods. Here is a plot focused on Venice, Italy. At the bottom left here, the blue curve here represents the observed sea level rise on the basis of tide gauges in Venice. The lighter blue curve is the reconstruction. This is the reconstruction of how global sea level has varied over the 20th century applied to Venice. And you will notice that there's a difference there. The actual observed sea level change in Venice was a higher sea level rise than the reconstruction, and that's tipped us off. because then we asked ourselves, why is the reconstruction wrong here? What local effect might produce that? The curve here at the top left here shows what that effect is. It turns out that the land has been subsiding in Venice locally, which has given rise to an increase in the sea level rise above what the reconstruction estimated. And why has it done that? It's done that, but since the 1920s, Venice has been pumping water out of the ground, and that pumping of water out of the ground has led to a subsidence of the land and a local, very local increase in sea level rise that couldn't be captured without global analysis. In fact, it's a very interesting point because now one of the ideas that's being thrown around to rescue Venice from this inexorable sea level rise is to pump water back into the ground. There are various engineers that are exploring this possibility, and there's arguments that you might be able, for example, to lower sea level by as much as a foot or 12 inches if you pump water into the ground and fill up the groundwater aquifers. The problem, though, there is you're not going to pump salt water into the ground because it will, of course, contaminate any freshwater aquifers. Okay, I have the last couple of slides here now to talk about what most of you might be most interested in, and that is projections of sea level into the next decade or century. This is work at its infancy now here, and it is very difficult. I must say that most of my focus is not on projections. I look backwards in time. But these projections are complex because they involve deep uncertainty. There's a limited amount of data. The data is not always reliable. There's a inconsistency in the information, which Daniel Ellsberg 60 years ago called ambiguity, etc. And that means that it's not possible at this stage to say, for example, to put out a probability distribution and say, this is what Boston might experience in the next 30 or 40 years. There's just too much uncertainty that these probability functions can't rigorously be developed. And there are some examples. I think Fiamma is going to talk about some of this, but the Antarctic ice sheet is often a focus of discussions of deep uncertainty because there are some basic elements in ice sheet stability in a marine setting, which is what West Antarctic ice sheet is in, that we don't fully understand the physics of ice sheet stability. And there are arguments about things like the ice cliff instability that are empirical, but not really based on any obvious physics. In the case of Greenland, there's uncertainty in the physics of calving fronts. So without a deep understanding of the physics, it's going to be hard to project sea level in any rigorous way, but people are trying, right? This is an example of a paper I'm not involved in, led by Bob Kopp, who's a colleague of mine and a colleague of Harvard. He's often up here to speak and to talk to his colleagues, where they've tried to put together a program or a platform called FACS, which breaks up each of these contributions in modules. And you can literally click on each of the contribution and pick a different prediction, for example, one that I might have produced for the Antarctic ice sheet in the 21st century or somebody else, or a different climate model to come up with at least some range of projections that you might be interested in considering. And these are sorts of examples of that. On the left here are projections using a low emission scenario for Greenland ice sheet contribution, Antarctic glaciers, and ocean dynamics to sea level change that would be experienced in New York City over the next century. On the right is the same thing, but these are projections of sea level experience that is expected to be experienced in New York City under a much higher emission scenario, SSP 8.5. And you can see there's variability that reflects the uncertainty that I'll talk about. But one of the most important aspects of these projections is trying to understand the possible frequency of extreme sea level events. And that's really where the power of these projections are going to come in. At the top, this is a discussion of a projection of extreme sea level return periods under a low emission scenario, and the bottom one is under a high emission scenario, both for New York City. How do you read these things? Well, let me look at this point here. This is under a high emission scenario. It says that an extreme sea level event that will raise sea level 2 meters will happen if at sort of current climate, or actually climate in 2000, once every 100 years, right? Yet as we move to 2050 and 2100, you'll see that the frequency of those events increases, so that by 2100, at a high emission scenario, that same event that would happen once a century or once 2 centuries will happen, according to this projection, once every 3 or 4 years, which is disheartening to say the least. And so I'm happy to talk more about these projections when we have an open discussion. I hope I haven't taken too much of my time allotment.
Thanks. That's just thanks. That's just fantastic. That's really interesting. I have a zillion questions, and so there are many in the submitted queue. But we're going to go over to Fiamma now, and then we'll come back to the Q&A section.
Great. Thank you, Jim, and thanks, Jerry, for a great presentation. Let's see if I can do this. Okay, so my name's Fiamma Straneo. I'm a physical oceanographer. And so as sea level rises or drops, because we're next to the Greenland ice sheet, I get to hang out on boats. So I'm going to go up and down with the rising sea levels. But that's what I do, is make measurements in places where we don't have a full understanding of the system, and really need to collect more observations to inform our understanding. And so here it's August 2023, and we're at the margins of a small glacier in Greenland. So Jerry showed a sea level rise, a global sea level rise curve. This is another one. And I just want to make the point on the right, so you can see, well, you can see the last 140 years. But when we talk about sea level, we have to be really careful about an attribution, as Jerry showed, what is driving sea level. And so on the right, I'm showing a pie chart. This shows what the dominant contributors to sea level rise over the last 20 to 30 years are. And so dark blue is the ocean expansion. So you warm up the ocean, you increase its volume. That will drive up global sea level. Everything else is really dominated by land ice. And so melting of Greenland, Antarctica, and glaciers in the Himalayas, in the Andes, and in the Arctic region. And glaciers, again, have dominated in the last few decades. So that's another third of sea level rise. And Greenland and Antarctica only account for 1/3. Greenland is roughly twice the Antarctic contribution right now. So this is to give you an idea. But if you can think back in time or think forward in the future, you would see different contributions to global sea level rise, a different partitioning. And so one of the challenges here is sea level rise is really a composite of all these different contributions, and you want to get them all right if you're going to make projections. In the future, in the long term, Greenland holds about 7 meters of sea level rise, Antarctica 60. Glaciers only hold about 0.4 meters. So in the long term, we can expect them to become less important. But this issue of long term is really an important question, and we should always keep in mind time when we talk about Greenland collapsing or West Antarctica collapsing, because there are time scales over which this will happen, and they can be very different. So I'm going to talk about ice sheets a little bit. Both Greenland and Antarctica are losing ice. This is a remote sensing, so satellite-based reconstruction. Greenland on the left, you can see red means it's lost ice. And so all around Greenland, the ice sheet is shrinking, and especially at the marine margins. Antarctica is different. Antarctica is isolated by a large-scale ocean current. It is much colder. And temperatures over Antarctica haven't increased dramatically as a result of anthropogenic warming. But the ocean has changed. And so Antarctica, you're seeing that the mass loss, it's concentrated in a few key areas. The West Antarctic region, the Amundsen Sea, and also the West Antarctic Peninsula. And on the bottom right, it's the contribution to sea level rise expressed in mass loss. And again, Antarctica is about twice Greenland, and you can see this cumulative loss. So what's happening? Why are they losing mass? Well, there's two ways that a marine ice sheet, so an ice sheet that terminates in the ocean, like Greenland or Antarctica, can lose mass. The first one is quite intuitive. If you increase the air temperatures, you can drive a net increase in melt. And so picture on the left, if you fly over Greenland in the summer, you're going to see a lot of melt ponds like this. There's a lot of melting, and this melting has been increasing. This accounts for about half of the ice loss for Greenland. The other type of ice loss is a lot less intuitive, but ice is moving from the center to the margins of the ice sheets. Eventually it forms icebergs that carve into the ocean. And so one of the things that has been happening in Greenland, and the dominant contributor to ice loss in Antarctica, is a speed up of these glaciers. And here I'm showing a zoom in. Red, the plot on the left just shows the speed, but the plot on the right shows the increase in speed, red. And so here are some glaciers or ice streams in Antarctica, West Antarctica, Pine Island, Thwaites. They're in the news very often. Thwaites, I think, has been named a doomsday glacier. They're speeding up. So they're taking more ice from the center of the ice sheet and putting it into the ocean. In Antarctica, this is the dominant contribution to ice loss. In Greenland, it accounts for roughly the other half. And so what is driving these changes? Well, I already mentioned in Greenland, it's an increase in the air temperature. It's driving an increase in mass loss. You've probably heard of Arctic amplification. This plot just shows the mean of Arctic air temperatures collected over land over the last century or so. And so the Arctic has warmed. The dynamic change, this glacier speed up, is thought to be largely driven by changes at the region where the ice meets the ocean. And so this particular image is a reconstruction from Antarctica, but Antarctic glaciers terminate in the ocean. They have these floating ice shelves, and these floating ice shelves buttress the ice flow. In other words, if you remove them, the ice behind them will flow faster. This is true in Greenland too. These floating ice tongues, they tend to be smaller, tend to buttress ice flow. So if you increase melting by the ocean or through some other process cause the disintegration or the reduction of these ice shelves, then the ice will flow faster. And this particular schematic shows on the left conditions maybe in pre-warming world, and on the right you see CDW is just an ocean water mass, but more warm water reaching the underside of this ice shelf, driving more melting. The ice shelf shrinks and the ice behind it moves faster. The process on the right, the increases melt, we don't know how to do it perfectly, but models can do it relatively well. The process on the right, this increase in the speed of glaciers and ice stream in response to a change in the ocean or a change at the ice-ocean boundary due to shrinking ice shelves, is very hard to predict and involves understanding a lot of physics that we are only now starting to catch up on. So we have projections. I don't expect you to read these lines. These are in the last IPCC. The top is Greenland. The lower one is Antarctica. And you can see there's different scenarios. And on the right, you see where the ice is being lost. Again, in Greenland, it's all around. And for Antarctica, it tends to be localized in some regions. The projections, you can see them out to 2100 are somewhere in the range of 5 centimeters to 10, maybe 20 centimeters for each ice sheet combined. And then you can see different estimates based on different methods. So we have efforts undergoing that are really trying to get at projections of ice sheet, but they're difficult because this ice-ocean boundary, which is where I happen to work, is really a difficult place where to make measurements. It's a very difficult place to model. And so I'm just going to show you some photographs to convey a sense of scale. This is one floating ice tongue, one of the largest ones in Greenland and Northeast Greenland. And this is a picture we took, well, somebody took of us several years ago. We're sitting in a rift and we're making some measurements. And these were the first measurements through this ice shelf, floating ice shelf made. And this was 2009. To predict the change for this ice shelf or floating ice tongue, we'd like to understand how the ocean temperature changes under the ice. And it's a difficult thing to do. And models, unfortunately, are not going to help us. Even ocean models tend not to resolve the circulation in the cavities. This is another picture. We're working at the edge of a glacier in Greenland, and you see this large region of open water, and that little spot that looks like a fly is actually, it's us making measurements in what is a large volume of fresh water that had melted above sea level, but that was carried to the base of the glacier, and it's now coming up in this large hose plume. And this is very important for melting. And so, again, the scale of trying to understand these processes. What we're trying to do is understand how melting happens. How does melting change if I warm the ocean? How does melting change if I melt more at the top of the ice sheet? And as of now, most projections of ice loss from both ice sheets are based on ice sheet models that are not yet fully coupled to Earth system models. In other words, there is no direct communication between the ice and the ocean and the atmosphere. We have to almost carry any change in the ocean quickly over to the ice sheet model, run the ice sheet model, and go back and do it again. And this is an indication of the fact that ice sheet modeling is really at its infancy. There wasn't a lot of interest until things started to change very quickly. And now they've been changing faster than we can keep up in the modeling. But a lot of people are working on it. It's great progress. And so to give you an idea of the challenges, this is an example of some work we did for the AR6 report. And so this is one glacier, this is one fjord in Greenland, and we coupled it to an ocean model. And you can see as time goes by, the warming of the ocean waters is driving a retreat of the glacier up here, as well as of these other glaciers. And so Greenland has about 200 glaciers. And when we talk about ice loss from Greenland, we're summing all of these individual systems that have their own dynamics, their own topography, and hence some of the complexity. So I'm going to switch gears a little bit, in part because of some of the questions, and I'm going to talk very briefly about the overturning circulation. There is a connection, of course. Actually, there's more than one connection. As Greenland melts, and as Arctic sea ice decreases, we're putting more fresh water into the North Atlantic. The North Atlantic is a very sensitive region of our climate system. It's a region where we form dense water, and it's part of this Atlantic overturning circulation. And there are these key regions, the Nordic seas and the subpolar region, where some of the heat loss to the atmosphere makes these waters very dense. And so you have warm waters going poleward, they lose heat, and they come back as dense cold water. And there's this general idea that this system is potentially unstable. It's based on having a salt flux as well as a heat flux poleward. And if you change this, then you can start reducing convection, or the waters will start to become too warm for the circulation to be driven, and there's a positive feedback. And so there's the scientific community. There's a lot of attention every few weeks. I feel now there's a paper on the AMOC collapse, and I'm not going to do a full review here. I'm going to stick a little bit with what we know. We know from the climate models that the overturning circulation will slow down. This is the last IPCC report, or at least the climate models predict that it will slow down. You can see that the climate models do not agree in some cases, and depending on the scenario, the AMOC keeps slowing down or stabilizes. And then there are a number of proxy-based reconstructions. So this is an indirect measurement arguing that the AMOC is very weak. But they are not perfect, and there are uncertainties in the interpretation of these proxy reconstructions. And so this is one of the tipping points in the climate system that is often talked about. The expectation right now is that any dramatic change in the AMOC would take hundreds of years, and the general consensus is that it's not going to happen in a very short time. But again, there's lots of papers arguing that it's imminent. I want to, again, I'm an observationalist. We don't know the answer to the AMOC collapse, but we need to understand the system better. Part of why we don't know the answer is we can see this instability in very simplified models, but it's difficult once you start putting all of the ocean atmosphere ice sheet complexity in. And so I want to point to two efforts. When in doubt, you just start measuring. And this is very important in our climate system. If we had started some of these measurements 50 years ago or 30 years ago, we would have more answers now. And so I want to point to two efforts of measurements of the overturning circulation. The top one is at 26 North, so sort of southern Florida across the Atlantic, and it's the rapid array, and it's been going on for since 2004. And the overturning is this red line. And again, every few years, there's a paper that says, oh, based on this, it's slowing down, or, well, maybe it isn't. But we've learned a lot from these measurements. You can look at the scale of variability of this overturning and see that it's very large, even on a daily cycle. The second one is an effort I'm involved in. It's actually measuring the overturning in the subpolar region. This is the representation of the currents, and these are moorings that are there. So imagine an anchored set of instruments that ends below the surface so that we can actually measure this transport. And this effort has been going on since 2014, so it started 10 years later. It is in a key location because we're not just measuring the overturning, but also the dense water formation and how these waters get exchanged with the currents around the Atlantic. And so we are learning a lot about this system. We are seeing a lot of discrepancies between the models and what we observe. And the hope here is we're working with the modeling community to really try and make sure that the models we're using are actually reproducing the observations and are able to capture the kind of physics that we think we need to resolve. And so with that, I'm gonna end and give it back to Jim.
Hey, that is great. Thank you so much. I'm going to start out. We have a number of pre-submitted questions, and let me remind the audience that this is a great time. If you have some questions, just drop them in chat. I have a few questions of my own. I actually have many questions of my own, but I won't stick with my questions. I will make sure I go through the pre-submitted questions and then keep my eye. I'm sorry, I misspoke, not on chat, but in Q&A, and I'll keep my eye on the Q&A. Okay, so I'm going to start with just like let's just get some basic things that might have gone really, really quickly. Okay, so Fiamma, you said AMOC and Atlantic Meridional overturning and so forth. Are we talking about the Gulf Stream? Is that sort of what the deal is here, or is there a little bit more to that than the Gulf Stream?
I mean, I think for many it's equated. It would be the Gulf Stream slowing down, although the Gulf Stream itself is more than just the overturning circulation, any system of currents. This is an oceanographer's response. It's driven by many things, and the Gulf Stream is part of that.
Got it. Okay, so it's related to it, and that's a piece of it. And presumably, this wasn't part of your discussion, but presumably slowing down means that we're changing the heat transfer system around from the tropics up to the northern Atlantic and so forth, and that could have substantial changes in the weather and the climate in northern Europe. Is that right?
That's correct. So reducing the overturning circulation or even shutting it down will have major, it's a very large heat transport system in our climate and will have large implications, not just for, let's say, Northern Europe or the Northern Hemisphere, but for really much of the globe. Yeah.
Got it. Okay, that's great. Another set of just basics here. So Jerry, you went really quickly over thermal expansion and ocean dynamics. Could you just give us like the little primer on what you mean by those two components? You mute. Unmute.
I'm muted so I wouldn't interrupt Fiamma. Well, thermal expansion is simply the expansion of ocean water through warming. There is a system of floats called Argo. I think there's several thousand of them. Fiamma may know more about them. And they go up and down in the ocean every day and measure temperature variations. And so water, like most substances, when warmed, it expands. Doesn't change the mass of the oceans, but does change the height of the oceans. So that's one. Ocean dynamics is simply wind-driven, largely wind-driven, don't want to upset Fiamma, a circulation in the ocean. As climate changes, as winds change, as buoyancy in the ocean changes, water will move around in a different pattern. Ocean dynamics and thermal expansion don't add mass to the oceans the way glaciers and ice sheet melting do. They move it around, and in the case of thermal expansion, just expand the column.
Got it. Okay. That's really helpful. Another sort of just stepping back for 1 second. So you spent some time explaining how we have an improved understanding of the rate of increase of sea level rise, that is the acceleration of sea level rise. Just why is sea level rise accelerating?
Well, I mean, all of the mechanisms that Fiamma touched upon are being driven in an amplified way. You're warming. Fiamma talked about these marine settings. A warming climate means you're warming the temperatures above ice streams, you're warming ice shelves, and you're warming water below them. So you're causing an exacerbation of a melting process. In Greenland, where Fiamma talked about the freezing, the surface mass balance increases, the undersea area of the ice streams warms, and you're essentially just accelerating all of those processes of melt. And if you even think about it, it can be quite simple. If you're melting an ice sheet and its surface is moving down, it's moving to warmer and warmer temperatures. So there are these nonlinear feedbacks that produce an even more accelerated process.
That actually gets to a more complicated question I was going to ask later, but maybe I'll ask this now of Fiamma. So one thing I've heard, and again, I'm an economist, so what do I know about this stuff? But you mentioned tipping points. Is there a point at which, the Greenland ice sheet is melting and melting and melting? Is there and we think, well, gosh, if we're able to stop emitting and stabilize temperatures around, let's call it 2 degrees, that then, I don't know what, is there a point at which the Greenland ice sheet gets so small that it simply is inevitable that it will totally melt, which of course it has in the paleo history, or can you explain this concept of that, and again, just stepping back, this tipping point idea is like there's this point of no return where once you've crossed it, there's nothing you can't like refreeze the ice once the ice sheet's gone. But can you explain a little bit of that?
Yeah, so there are a number of processes which tend to self sort of amplify, and we call them positive feedbacks. One of them is the one you just mentioned, or Jerry mentioned, which is that in part the ice sheet survives because it's really cold. If you take a measurement through the atmosphere, it's kind of warmer near the sea level and progressively gets colder. And so the ice sheet is quite tall. In Greenland, it's several thousand meters tall at its tallest. And so the air is very cold up there. As you start melting, as you start warming the air temperature, then you're going to melt the top of the ice sheet. At times, it's happened, 2012 melting all over Greenland. And so you lower the elevation. Well, now a lot of the ice sheet is at a slightly lower elevation. So if you warm again, you have increased warming, maybe you'll lower it again. And so the ice sheet can't quite keep up. It's a positive feedback. There are other positive feedbacks. The other one is if you increase air temperatures, you generate maybe these melt ponds. These melt ponds attract more sunlight or at least absorb more sunlight. The albedo has changed. They're not as reflective as white snow. And so again, once you start melting, that's another potential positive feedback for the ice sheet. And in Antarctica, there are other tipping points. People call them tipping point. There are these positive feedbacks, which have to do with once you get a warm water in the cavity, you start melting more. You might drive more warm water in, or instabilities of the ice itself, marine ice sheet instability, marine ice cliff instabilities. And so they are listed as tipping points. I think the thing to remember is that very often a tipping point is described by local processes. I warm the temperature above the ice sheet and the ice sheet shrinks. And in reality, Greenland and Antarctica are embedded in the entire climate system. And so we have some tipping points, but really we should think of them as processes that can amplify and can lead to rapid change. Once they're embedded in the entire Earth system, though, it's very complicated, just like the AMOC, the Atlantic Meridional Overturning Circulation, to actually predict how things will go, because we have to understand the change globally. So I rather rephrase it. Instead of thinking about tipping points, I think as we should be worrying because we see trends, and in fact, they're not steady trends. The rate of increase of ice loss from Greenland and Antarctica is increasing. The rate of air temperature change is increasing, and we should be worried about positive mechanisms that will amplify this change without really thinking about, I'm going to fall off a cliff. We don't need to fall off a cliff to be worried about the climate change that's happening.
That's really an important observation, that the tipping points are an interesting thing to think about, but that there's sort of not but it's important to remember the process is getting worse or getting more severe without the tipping points. There's a really interesting question on this topic that was pre-submitted from paleontology or paleoclimate records. We know that there are periods in the past when sea level rose by a foot a decade. What's the likelihood of that happening again?
Well, okay, so a lot of my research involves paleoclimates, and if you want to understand what ice sheets are going to do in a warming world, one way to do that is to run climate models. The other is to look backwards in time and ask in other previous periods. Now, wow, foot in a decade. So there are cases, 14,000 years ago, there was a case called Meltwater Pulse 1A where sea level rose 20 meters in a couple of hundred years. But there was a lot more ice around, right? 14,000 years ago. Canada was still largely covered by an ice sheet, and all the mechanisms that Fiamma has mentioned would have been active then as well in the marine settings, et cetera. And so you just had a lot more ice around. In periods where we were in interglacials, that is a period like today when we're at sort of at minimum ice levels. The last one was 120,000 years ago. And we do know as scientists by exploring sea level then that global mean sea level was probably around 6 meters higher than it is today. And the precision in that magnitude is good, but we don't know exactly how long, what time scale it took to raise sea level by 6 meters above present day levels. That it take the whole interglacial, that is 7 or 8 thousand years, or did this happen in a kind? And Fiamma and I both seem to have a discomfort in using the word tipping point, but let's imagine that at some point in the interglacial 120,000 years ago, you might have had catastrophic collapse. But that's still to be figured out. But the really high numbers that people cite, those are periods in which there was much more ice around.
That's great. That's really interesting. We've had a number of questions on the financial side of things, and I'm not going to answer that, but I will give people references. If they go to the website of the Environmental Protection Agency and look up documents on the social cost of greenhouse gases, one of the elements that was used to calculate the social cost of carbon was actually the financial consequences of sea level rise, and they have some estimates there. But more importantly, they have a really good bibliography and citation sets, and it's quite accessible. Okay, back on there's a lot of questions on the adaptation side and the specific implications. So one is like, what are the most vulnerable cities in the United States, and how do we, how pressing are these questions for some of our cities?
Fiamma, I can talk about that a little bit, right? I mean, vulnerability, see, I talked about projections, and projections are stated to 2100, but really what the term that's often used in discussions is policy relevant projections. Those have timescales of, I don't know, in the US, 4 years, 6 years, 10 years. And within that time frame, the uncertainty comes in extreme sea level events, right? We understand that from what happened to New York and New Jersey just a few years ago. It is quite difficult to project the vulnerability over those sorts of timescales because an extreme sea level event might happen or it might not happen within that 5 years or 10-year period. But I don't think it surprises anyone that places like New York City, which are they're implementing a lot of interesting adaptation policies. Places like New York City, the Chesapeake Bay area, these are areas, New Jersey, of course, Hurricane Sandy, all of these highly populated areas have a strong element of vulnerability. I will tell you that if the Antarctic ice sheet were to melt rapidly, the highest sea level rise on the globe would happen just off the coast of Washington, D.C. So that's a disheartening possibility. But it really, to understand vulnerability, you really have to understand when and where these extreme sea level events. And the other thing that makes those predictions hard to make is that when that storm surge comes in, were you at high tide or were you at low tide? So you can just get unlucky because those two things can differ by just a few hours. Hard to say, but any low-lying city on the U.S. East Coast, certainly New York, Washington area, Chesapeake Bay area, New Jersey, they're all vulnerable, as is obviously Florida is the one that's often discussed. I think Fiamma and I have once discussed Georgia as well, Fiamma, in another conversation. So I wouldn't say there's anywhere that is really free of vulnerability.
Another question has to do with just going back to the basic science. So both of you stressed things that we sort of a lot of uncertainty about. If you had your ability to whatever disperse NOAA or NSF funds or whatever and think about what the scientific priorities are, sort of what's the most important set of measurements beyond just what you are able to do with your research in your labs. What are the most important things that we collectively need to learn scientifically to be able to make this sort of projections? And, let me just make one quick comment. Yes, of course, the political time frame might be 4 to 6 years, but major institutions, is Harvard worried about this? Well, gosh, we have some properties. Our time frame is 50 years, 100 years, 75 years. So I think one can think on much longer time frames than just the 4 to 6 year time frame. But what's the science that we need to be doing to get a better handle on this?
So Fiamma can talk about observations. Fiamma, I'll talk about modeling.
Okay. I mean, I think again, it depends on time scale, and if we're interested in the next 10, 50 years, as Jerry said, I think the largest costs in terms of priorities, maybe even national priorities, is from extreme events. These will be some of the largest, whether this be hurricanes or flooding and so anything that can help, and so a lot of this doesn't have to do maybe with ice sheets, or it doesn't have to do it has to do with a lot of atmospheric dynamics and ocean dynamics, and so trying to increase the observations both in the ocean, the atmosphere, the model's ability. On longer time scale, if we're talking ice sheets, we're very interested in calving. So the breaking off of icebergs is something that we don't fully understand. And so there are many systems now of observing the full cycle of a calving event, maybe by putting a autonomous system that continuously scans an ice front. And one of the large unknowns also on the glacier size is trying to understand, and I can say this because I'm an oceanographer, so this doesn't benefit necessarily me, it benefits my research, but I wouldn't apply for this funding if you wanted to give me any money for this, is to understand there's all this increased surface melt at the top of definitely Greenland, and how this water travels through the ice, where it goes, whether it fractures the ice more is a really tough question, and one that we need to understand. And so I think it's really important to get observations that are going to help some of the ice modeling, which is farther behind than some of the other modeling we're doing.
Yeah, I think Fiamma's presence at Harvard, it tells you something, and that is that even a modeler like me recognizes that observations are going to be key to this. There are various initiatives going on at Harvard now to bring in more people that have expertise in observations. But on the modeling side, that's also important. When I talk about deep uncertainty, I mentioned something, and Fiamma also mentioned the marine ice cliff instability. This is an idea that holds that an ice cliff at the ocean ice sheet interface cannot be more than 100 meters in the Antarctic before it'll start falling like a domino. And if that happens and you move to deeper water as you go back, it's all just going to collapse. Well, the physics of that is unclear. Whether that will really be active or not is completely unclear. And yet, if it is active, it would make a very significant difference in projections of sea level rise. And Fiamma also mentioned calving. Calving physics is uncertain. So when I think of deep uncertainties, I also think of really about fundamental physical questions in climate science that haven't been fully worked out.
Well, we could keep this going for a long time, and I have plenty of questions on the list, but unfortunately we are out of time. So I need to thank both of you. This has just been fascinating. Thank you, Jerry. Thank you, Fiamma. And thank you to the audience. Thank you to the folks who put this together and Harvard Alumni Association for making this happen. We're going to be back next month with another episode. And until then, have a nice Thanksgiving and good evening.
Bye-bye.